Part 4 of Unit 12 is about Kb, the equilibrium constant for bases. Okay, let's talk about weak bases. Bases react with water to produce a hydroxide ion, but these are going to be ones that don't dissociate completely. We're going to have a new dissociation reaction. Our base plus water is going to be at equilibrium with Hb plus OH minus. So here, Hb plus, that is our conjugate acid, and OH minus is the conjugate base. So this is our general form for the dissociation of a weak base. Let's try to solve a problem to find the pH of a basic solution. What is the pH of a 0.15 molar solution of ammonia? The Kb of ammonia is 1.8 times 10 to the negative fifth. Well, let's write our reaction. Our base plus water at equilibrium with ammonium, our conjugate acid, and hydroxide, our conjugate base in that reaction. So our equilibrium constant, since we're using bases, it's Kb instead of Ka, is going to be the ammonium concentration times the hydroxide concentration divided by the ammonia concentration. Again, we're going to leave out water because it's a pure liquid. So here's my rice table, and once again I left water out of it because it's pure liquid. It's not going to have any values in the rice table, and I just left it off of here to give me more room to write actual numbers. Our initial concentration of ammonia is 0.15. It's at equilibrium with these two. We're going to assume that there was no hydroxide or ammonium present at the beginning. We know that Kb is equal to 1.8 times 10 to the negative fifth. So let's try to fill out the rest of our rice table here. Everything is a coefficient of 1, so we have plus x for the products. So at equilibrium they're just going to be x, and minus x for ammonia, the reactant. So at equilibrium it'd be 0.15 minus x. The same way we had the weak acid assumption, we can use the weak base assumption. We could say that 0.15 is so much greater than x that our equilibrium concentration is going to be approximately 0.15. It would round back up to 0.15. We can do that because we've got an exponent of negative 5 in our Kb. So as long as we write this information right here, we're showing that we're using the weak base assumption, and we can take this minus x out of our rice table. So now we can solve for x. 1.8 times 10 to the negative fifth is equal to x squared divided by 0.15. When you solve that, x is equal to 1.6 times 10 to the negative third. Again, that's not the final answer to the question. We know that at equilibrium, the hydroxide concentration is 1.6 times 10 to the negative third. Well, we can find POH by doing the negative log of the hydroxide concentration, 1.6 times 10 to the negative third. When we do that, POH is equal to 2.78. Now that's not the final answer to the question either, because they're asking for the pH. You're not going to find very many questions that ask specifically for the pOH. So what we need to do, let me erase some work over here, give myself some room to write, we're going to use the pOH to find the pH. Because we remember that pH plus pOH is equal to 14. Well, if we plug in our pOH here, 2.78 plus the pH is equal to 14. We just have to subtract from 14. So our pH is going to be equal to 11.22. That's our final answer to this question. So we used the weak base assumption to make our math a little bit easier, and they gave us the Kb, so we used all that to solve for X, which was the hydroxide concentration. We found POH and converted it to pH for our final answer. There's a special relationship between Ka and Kb. Ka times Kb is equal to Kw, 1 times 10 to the negative 14th. So, if you know one of them, you can always solve for the other by dividing Kw times the thing that you know. Your question for this section, the pH of a 0.6 molar solution of methylamine is 12.21. Calculate Kb for methylamine.